Now, what will you gain after studying this module? You will be able to understand different rules by which absorption maxima is calculated. You will understand the basics of absorption laws. You will understand the application of these absorption laws and the deviation observed. Now, to begin with, let us try to understand what are these Woodward-Feiser's rules for calculating absorption maximum, that is lambda maximum. Let us first try to understand these rules and then we would be applying these rules. The scientist named Woodward in 1941 studied number of compounds, especially organic compounds, and deduced certain rules for calculating lambda maximum for particular molecular structure. These rules were then modified by another group of scientists by the name Scott and Feiser. And since then, these rules are known as Woodward-Feiser's rule. The values calculated by these rules generally lies within the 2 to 3 nanometer of experimental values. According to these rules, each type of absorbing system like dyne, triene or polyene has a certain fixed value at which absorption takes place. This value is called basic value or the parent value. The contribution made by various substituted groups or rings which are attached to this system are then added to this base value to get the final value of absorption maximum, that is lambda maximum. Now, what are the parent system that we would be considering? The parents values of various system and contribution of various substituents now are, to begin with, we would be considering conjugated dynes. Now, to understand conjugated dynes, first let us try to understand what are the various types of dynes or we would be considering. Now, these dynes are acyclic dynes which normally are present in their transoid form. Then these dynes could be present in two different rings when it is called heteroannular dyne, and this dyne system could also be present in one ring only when it is called homoannular dyne. So, we would be assigning basic values to these systems by Woodward-Feiser's rules. For acyclic dynes, the basic value given is 214 nanometer. For heteroannular dynes, it is 214 nanometers, and for homoannular dynes, this base value or the parent value is 253 nanometer. Now, there are fixed nanometers which we would be adding to these various assigned basic values. For alkyl substituent, 5 nanometer is added. For each alkoxy substituent, the increment is of the order of 6 nanometer. For chloro and bromo group, the increment is of the order of 5 nanometer. For alkyl mercapto, that is SR group, the increment is of the order of 30 nanometer. For NN dimethyl group, Nr2, the increment is of the order of 60 nanometer. For exocyclic double bond, that is double bond which is present outside the ring, the increment is of the order of 5 nanometer. And we have actually considered Dyne system, and for each additional conjugation the increment is of the order of 30 nanometer. Now we will understand these by considering various this example. Here we would be considering the acyclic Dyne component as the parent system. So the value for the parent system is 214. Now we would consider the increments. As you can see, there is one alkyl substituents attached to the basic system and one alkyl substituent is attached to the additional conjugation which is there, or the extended conjugation. So the number of alkyl groups comes out to be 2. So increment is 10 nanometer, and for extended conjugation the increment is of the order of 30 nanometer. Adding the values, the value comes out to be around 254 nanometer. Now Woodward-Feiser's rule can also be applied to alpha beta unsaturated ketones or dinones or enones. Basic value for alpha beta unsaturated ketones is 215 nanometer, and that for aldehyde is 207 nanometer. Basic value for alpha beta unsaturated acids and esters is 195 nanometer. For cyclic enones, ene from unsaturation, one from carbonyl is 215 nanometer. Base value for 5-membered cyclic enones is 202 nanometer. Now coming to the increments. For double bond extended conjugation, the increment is of the order of 30 nanometer, and for homodyne component, the increment, as you can see in the figure, basic system is alpha beta unsaturated carbonyl component. There is one extended conjugation, but both the double bonds, since they lie in the same ring, it is referred to as homodyne system, and the increment given for this is 39, whereas no extra increment is given if the extended conjugation lies in two different rings. Now for alkyl group or ring residue at alpha position, alpha to alpha beta unsaturated carbonyl system is of the order of 10 nanometer. If this group is present at the beta position, the increment is of the order of 12 nanometer, and if it is present at the gamma position or higher position, the increment is of the order of 18 nanometer. Now, if the hydroxyl group is present at the alpha position, then the increment is of the order of 35 nanometer. If it is present at the beta or the gamma position, then the increment is of the order of 30 nanometer. If it is present at the delta position, increment is of the order of 50 nanometer. Now coming to alkoxy group OR. If it is present at the alpha position, the increment is of the order of 35 nanometer. At beta it is 30 nanometer, at gamma it is 17 nanometer, and if the substituent is OCOR, acyloxy group, Whether it is present at alpha, beta, gamma or delta position, the increment of the order of 6 nanometer is for chloro group at alpha, gamma or delta position, the increment is of the order of 15 nanometer. However, when this group is present at beta position, the increment is of the order of 12 nanometer. Similarly, for bromo group, if it is present at the alpha, gamma or delta position, increment is 25 nanometer, but if it is present at beta position, increment of 30 nanometer is given. For NH2, that is amine or substituted amine, NHR, if present at alpha, gamma or delta position, no increment is given, but if it is present at beta position, an increment of the order of 95 nanometer is given. Let us try to understand this in the example. Now, this is a system which is acyclic system, that is the alpha beta unsaturated carbonyl system is not present in the ring. So, the base value is 215 nanometer. Now, coming to the increments, as you can see, there is one substituent at the alpha position. So, increment for the alpha is 10 nanometer. One substituent is present at the beta position. So, increment is of the order of 12 nanometer. So, adding all the three values, lambda maximum comes out to be 237 nanometer. Now, let us try to understand the benzene ring, which is a chromophore, and the different substituent attached to the benzene. Base value for benzene ring is 246 nanometer. If aldehyde group is attached to the benzene ring, as in case of benzaldehyde, the increment base value is 250 nanometer. If ketone is attached to the benzene ring, base value is 246 nanometer. If carboxylic group is attached to the benzene ring, then the base value taken is 230 nanometer. For ester group attached to the benzene ring, base value taken is 230 nanometer. Now, coming to the increments, as we know, benzene ring, it can have three type of di-substituted products, that is ortho, meta or para. Now, if the group is attached at the ortho or meta position, and if the group is alkyl group, the increment is of the order of 3 nanometer. If the alkyl group is para to the substituted benzene ring, the increment is of the order of 7 nanometer. Coming to hydroxyl group or alkoxyl group, if again ortho or meta, the increment is 7 nanometer. For para, the increment is 25 nanometer. If on substituted benzene ring, chloro group is attached, at ortho and meta position, no increment is considered, and if this group is present at para position, increment of the order of 10 nanometer is observed. For bromo group, an increment of 2 nanometer at ortho or meta position and 15 nanometer at para position. For amino group, increment of 13 nanometer at ortho or meta position and 45 nanometer if present at the para position. For substituted amino group, for example, acetanilide or acetylated amino group, ortho or meta position 20 nanometer is observed, at para position 45 nanometer is observed. For dialkyl amino group, at ortho or meta position, an increment of 20 nanometer is observed, and at para position increment of 45 nanometer is observed. For monosubstituted amine group, at ortho or beta position no increment is observed. At para position an increment of 73 nanometer is observed. Now let us try to understand this table with the help of this example. As you can see, it is the basic system here is acetophenone, that is the ketonic group attached to the benzene ring. So the base value is 246 nanometer. Since there is one orthomethyl group which is present, the increment referring to the table is of the order of 3 nanometer. So the total lambda max comes out to be 249 nanometer. So you can appreciate these rules. We can predict the lambda maximum of a particular compound. Now let us try to understand the next aspect of UV visible spectroscopy, that is the laws governing UV visible spectroscopy. When electromagnetic radiation falls on a sample under study, some part of radiation is absorbed by the material, whereas the remaining part is scattered or transmitted. UV visible spectroscopy involves the absorption of light in the UV or visible region studied together of electromagnetic spectrum, which results in electronic transitions from ground to the excited state as studied earlier. The absorption of electromagnetic radiation is governed by some laws called absorption laws, which are, the first law is known as Beer's law. This law gave the relationship between the absorption of light and the concentration of the absorbing material. According to this law, when a beam of electromagnetic radiation passes through the absorbing material dispersed in a non-absorbing solvent, which is very important, then the absorption of radiation is directly proportional to the concentration of the absorbing material. That is, if we represent absorbance by A and concentration by C, then absorbance A is directly proportional to the concentration. Or we can commute it like this: we can calculate the absorption by considering the intensity of the incident light, that is I naught, and the intensity of the transmitted light, that is I. The difference between the two values will give us the intensity of the light absorbed. Taking the log, it will be A will be equivalent to log I naught upon I, that is A, and that is proportional to the concentration. Another law which governs the UV oblique visible spectroscopy is Lambert law. This law gave the relationship between the absorption of light and path length of the light in the sample or absorbing material. According to this law, when a beam of light passes through the sample, the absorption of light is directly proportional to the path length of the light in the sample of the substance, that is A is directly proportional to L. As explained in the previous law, A or the absorbance is log I naught upon I. So, log I naught upon I is directly proportional to the path length, that is L, which is taken in centimeter. So, combining the two laws, we get Beer's and Lambert law. This law states that the absorption of light at a particular wavelength of absorbing substance is directly proportional to the concentration of the sample C and the path length in the sample, that is L. So, log I naught upon I is directly proportional to L into C, that is length into concentration. Or removing the proportionality sign, log I naught upon I is equal to epsilon LC, where epsilon is a proportionality constant and known as molar absorptivity or molar extinction coefficient or simply extinction coefficient. So, Beer-Lambert law can also be written as A is equal to epsilon LC, where A is log I naught upon I, is also known as optical density or simple absorbance. Now, coming to the significance of proportionality constant, that is epsilon. Molar absorptivity is a constant which relates the absorbance A with molar concentration C and path length L in a sample. It can be expressed as epsilon is equal to A divided by C into L. It is a measure of intensity of absorption. Larger the value of epsilon, more is the intensity of the absorption, and the value of molar absorptivity ranges from 0 to 10 raised to the power 6. Transition with molar absorptivity greater than 10 raised to the power 4 are called high intensity absorptions, while transition with molar absorptivity less than 10 raised to the power 4 are low intensity absorption. Units of absorptivity. Since absorbance A is a dimensionless quantity, so molar absorptivity has units of liter mole inverse centimeter inverse. Liter mole inverse is the unit of concentration and centimeter inverse is the unit of length, path length to be more precise. Now, coming to the percent transmission of light. Now, since I upon I naught is the ratio of intensity of the transmitted light and the intensity of the incident light from the sample under observation, thus transmittance of the light by sample can be written as I upon I naught. The percentage transmittance can be written as I upon I naught into 100. So, these rules they govern the absorption of a particular substance, but not all the substance or the sample under observation follow this rule. There are certain deviation from Beer-Lambert law. So, under certain conditions, Beer-Lambert law fails to maintain a linear relationship between wavelength and concentration of analyte. These conditions can be categorized into three categories. First is real, that is, these deviation can arise because of limitation in the law itself. Then next is chemical. These deviations are observed due to specific chemical species of a sample which is being analyzed. Third deviation can arise because of instrument. Deviation which occur due to how the attenuation measurements are made. Beer-Lambert law is strictly followed in case of single species. However, if a sample contains a different structural form of the same molecule in equilibrium with each other, such as the keto-enol tautomerism, where the keto form of a molecule is in equilibrium with the enol form, this law is not obeyed. Further deviation from the Beer-Lambert law are also observed under the following conditions. Number 1. This law is not applicable if solute sample and the solvent sample interact with each other to form a certain kind of complex. Deviation from Beer-Lambert law are also observed at high concentration of the sample, because under these circumstances high electrostatic interactions are observed. Deviation from the law are also observed by scattering of light by sample. Next, deviation from Beer-Lambert law is also observed in the case when non-monochromated radiations are used. Still another factor, deviation from Beer-Lambert law are also observed if sample undergoes a photophysical change, such as if it shows fluorescence or phosphorescence. To summarize what all we have studied in this module, we have calculated the absorption maximum for various absorbing molecule by following Woodward-Feiser's rules. You can have the practice of this by taking various examples from either from the book or you can download it through net. The absorption of UV visible spectra is governed by Beer-Lambert law, which states that absorption of a light at a particular wavelength of the absorbing substance is directly proportional to the concentration of the sample and the path length of light in the sample. That is, A is proportional to C into L. Molar absorptivity is a measure of intensity of absorption. Larger the value of epsilon, more intense the band we would be observing in UV spectra. Beer-Lambert law is strictly followed in case of a single species. However, if the sample contains structural forms or high concentration, this law is not obeyed.